mixing together. Here you have sodium. Now sodium is a metal. It's solid at room temperature. It's very, very reactive. It actually will start to look like it's tarnishing when it's exposed to air, so you have to store it properly. If you look at chlorine, chlorine is a gas at room temperature. If you look at it, it's red on the periodic table. It's a gas at room temperature. It's poisonous, right? So obviously you don't want to breathe this in. Now both of these combined make salt. Table salt, which you use to season your food. So you have something that's extremely reactive, something that's poisonous, coming together. One's a solid, one's a gas, comes together to form salt. And if you look at salt, it's tiny little crystals, right? So their properties are way different. You cannot assume just because, oh, it happened to be, gas as an element, it's going to stay a gas as a compound. Completely different. So you'll notice its properties are not even remotely the same. When we look at compounds, here you have a particular mixture, right? Now, when we look at mixtures, right, what are the two types of classifications you have? Yeah, homogeneous and heterogeneous. So when you look at a mixture, right, you have these compounds mixing together. Doesn't mean that they're going to necessarily react with each other. Now, when we look at a chemical compound, doesn't matter when we're looking at water in a container or a balloon or the water that you use to take a bath, right? If we look at the chemical formula, it will always be the same. It's always H2O. Yes, water has other things in it, other minerals in it, but the actual chemical formula for water is still H2O. And the ratio is the same. If I look at this number is called the subscript. This number tells you the number of hydrogens. There's no number here because what's the number that's indicated there but we don't show it?
1.
Yeah, 1. So 1 is there. If you look at it, you have 2 hydrogens for every 1 oxygen. So when we look at this always tells you the relative number, but it will not change. So this is just telling you that when we look at law of constant composition, when we look at different masses, the actual ratio between the elements stays the same. Let me show you an example here. Here I'm comparing the mass. You have 18 grams of water. You decompose it, break it apart. Because if you look at it, H2O is made up of hydrogen and oxygen. You're breaking that apart. You have 16 grams of oxygen, 2 grams of hydrogen. They want the mass ratio. So here we're looking at the mass ratio. Now it doesn't matter how much water I use. This was 18 grams. I could have used 3 billion grams. The ratio between the oxygen and the hydrogen, the mass ratio, will always be the same, 8:1. So it doesn't matter if I have 500 grams of water. When it decomposes, it's always going to have a ratio of 8:1 every single time. It's mass ratio, not its atom ratio. Its atom ratio is 2:1. But this is looking at mass ratio. Because what's easier to measure? Mass or counting atoms? Mass, yeah. So you'll see the mass ratio being used. So this was what I was saying. Right, H2O, you have the symbol. The subscript tells you how many hydrogen atoms you have. Again, Anytime there's one, we don't indicate the one. You're going to just see the symbol and then that's it. If it's any other number, it always has to be indicated. And it's always whole numbers. You're never going to see 2.5 or 1.0. You'll never see that. So it's always whole number ratios every single time. Now, when you're looking at this, there's a method to the formula, meaning there's a reason why hydrogen is first, then oxygen. It's not the other way around. It's not oxygen, then hydrogen. When you look at sodium chloride, there's a reason why it's sodium first, then the chloride, the chlorine part. It's not the opposite. There's an order to it. It's just not random when you do this. So when we look at chemical formulas, the most metallic is named first. So that's why sodium is first. The sodium is the metal, chlorine is the non-metal. So you'll see that sodium chloride, sodium bicarbonate, which is baking soda, same thing, sodium's first. If you're looking at a single column, meaning you have non-metals, you're dealing with this side here. When we look at this, the way it works is from the top up. So here you have sulfur dioxide. So if you look at sulfur and oxygen, they're in the same column. But when we name it, we work our way up. So sulfur comes first, then you have oxygen. So sulfur dioxide, it's not the other way around. It's not oxygen and then sulfur. When we're looking, let's say we're going in the same row, we go from left to right. So carbon dioxide, CO2, we say carbon first, then the oxygen, not the other way around. So you'll see that, carbon first, then oxygen. So if it's in the same row, it's left to right. If it's the same column, it's top to bottom. There are exceptions, and that you'll see here. This is an ion. Notice it's OH. This ion is called a polyatomic or diatomic ion. Diatomic meaning two. Diatomic ion. So that's the one that's unusual in that sense. If you look at it, it's OH, but then when they name it, it's hydro first, right? We're talking about the hydrogen first, then the oxygen. But here the order is opposite. So that's the only exception. Oh, this was a listing for the non-metal. So you'll notice again, carbon first, carbon dioxide. Carbon comes first, and then the actual oxygen. Now this, you don't need to memorize or anything like that. The name, when it's provided to you, you just name it in the order it's provided to you. Meaning, if I write down, spell out sodium chloride, the first element that you're going to write out will be sodium. Then the chlorine part, which is the chloride. You're not going to put Cl first. That's not in the order the name is written. So there's no point of trying to memorize it. The way it's written will help you determine the order. Carbon dioxide. Again, the only exception is this guy, hydroxide ion. It's not oxygen first, it's hydrogen first. But the formula is flipped. Now, everyone's favorite. These are the culprits that my 101 students are not a fan of. Polyatomic ions. Okay, let's look at the name first. If I say polyatomic ions, what does poly mean?
Many.
Many, right? Here we're dealing with more than two, basically one. So let's look at the words. say monoatomic ion, mono means what? One. So that's something like this, the magnesium ion. If I say atom, that's just going to be magnesium. If I say diatomic ion, here I'm dealing with two atoms involved. Example of this, that hydroxide ion. Notice I have oxygen and hydrogen involved. And there's a charge. When I say polyatomic ion, here I have two or more atoms, atomic atoms involved. Example of this. Notice two elements are involved, nitrogen and oxygen, but how many total atoms do you have? 4. 1 here, nitrogen, and then 3 oxygens. You have 4 atoms involved. That's where you get into polyatomic, multiple atoms, and it's an ion. This is called the nitrate ion, which I'll show you on the next slide. Now, when we look at polyatomic ions, right here, there's nitrate. They behave as a unit. So these polyatomic ions are present in solution. Even monoatomic, you have them in solution, in water especially. That's how you get soap scum, that's calcium buildup. So there's calcium ions in your tap water. When it sticks to the glass, right, the water will evaporate. The calcium solidifies, and then that's where you get the soap scum from. So when you look at this, these polyatomic ions behave as a unit. You treat them the same way like you treat this magnesium ion. It will stay together. You're not going to break it apart. This will not break apart into nitrogen and oxygen. It stays intact. So it's a family that does not break apart, basically. You can't break it apart. And it has a charge to it. This is its net charge. Now in 101, you'll learn about how this charge is actually established. There's a method to it, and it's dealing with its geometry. So you'll see that. Now, when you look at this, notice how the formula is written. You have magnesium. How many magnesium atoms? Just one, because notice there's nothing indicated there. There's nothing here. There's a 1 there, but we don't indicate that. Now, notice how they're looking at this nitrate ion. You have parentheses, and there's a 2 outside of it, meaning you have 2 of these nitrate ions, 2 units of it. So here the relationship is you have 2 units of nitrate for every 1 magnesium. So they call this a unit or a group. You'll hear that word being used, a unit or a group. Now, if I'm looking at this formula, if I want to figure out the number of atoms, I can figure that out. You just have to remember that this 2 applies to everything inside of it. So, magnesium, you told me there's only 1 magnesium atom. How many nitrogen? 2 nitrogen atoms. And 6 oxygen atoms. Because you're carrying over that 2. It applies to everything in the parentheses. It's the same thing when you're doing math problems, right?
Just the parentheses, right? Just the parentheses.
Just in the parentheses, yeah. Same thing here. You want to distribute everything in the parentheses. But then if I have a number outside here, you don't apply that 2 to that 6, right? That's completely different. So that's like the magnesium. You keep it separate. So only inside the parentheses. So if I'm asking for atoms, you look at, okay, do you have some type of unit? And you'll know that by the parentheses. If you don't have parentheses, then you only have one unit of it. Meaning if you have something like this. So it's still nitrate, the NO3, you still have that. And then you have sodium, but no parentheses. So here, the ratio is 1:1. You have one nitrate for every one sodium. If I wanted to know atoms, you have one nitrogen atom, one, I'm sorry, I'm getting ahead of myself, and then 3 oxygen atoms. So here you don't have any parentheses to actually apply a number to it. It's just going to be 1, 1, 3. I'll show you the polyatomic ions and more information about them, but they are provided to you on your potentially useful information. I give you your polyatomic ions, but these are not all of them. These are not all of them. You'll learn a method where you'll be able to derive the other ones. And that's dealing with the number of oxygens, because if you look at it, all of them except the ammonium ion and the cyanide ion are the ones that don't have oxygen, or thiocyanate, but everything else has oxygen. So you're able to change the number of oxygens, and it changes the name of the actual ion. And they do exist like that, so you'll learn that method. This is what's provided that you're able to derive other ions from it. So you'll see that. Okay, when we look at formulas, we always say, oh, it's a chemical formula. Now, you can classify that chemical formula even further. You can have empirical formulas and molecular formulas. Example of this, hydrogen peroxide. Now, if you look at this, what's the ratio between the two?
1:1.
Yeah. Technically, if you look at it, it's 2:2, but can you reduce that?
Yes.
Yes, you can reduce it to 1:1. So if I look at this, they have different names to it. This is called the molecular formula, right here. This is called the empirical formula. So molecular tells you actual number of atoms that you have. Empirical tells you the basic ratio. And that's important to understand because you will have situations where this will happen often. So here, if you look at this, you have C6H12O6. What's a number you can divide all those subscripts by? 6, right? This is the molecular formula. This is glucose, right? And if you look at it, I can reduce everything. So that's the molecular formula. If I reduce it, it's going to be what?
CH2O.
Yeah, CH2O. Glucose is a carbohydrate. Carbohydrate, that's where they get the name. If you look at any of the other sugars, fructose, glucose, sucrose, which is table sugar, they all have the same empirical formula. They just build on it from this guy here. So they'll vary in the number of hydrogens, carbons, and oxygens. So it might be, instead of 6, it might be like 7 or 8, whatever it is. But you'll always see that variation.
What compound is that? C6H12?
Oh, glucose.
Oh, glucose.
Yeah. So this is the molecular formula, actual number of atoms. Empirical is the basic ratio. the lowest possible terms. So when we look at formulas, the first one is one that you're going to get familiar with really fast. That's the one you'll learn first, just the formula. Then once we get into chemical reactions, after that, we'll learn about structures, because the structure dictates a lot about its properties. So this is the structural formula where the lines represent that bonding. Is it ionic or covalent? Ball and stick model, this one gives you a three-dimensional representation, because remember, these atoms, these molecules, they're not flat, right? They're three-dimensional. So the shape plays a big role. The geometry plays a big role in chemistry. Math does, and regular algebra, but geometry plays a big role. Space filling gives you a much more accurate depiction, because this is relative to size. One thing you have to keep in mind, when we look at molecules, they don't have lines between them to represent bonds. You're not going to see that. It looks something more like this. So the space filling model, you'll see more in 101, where we get into what exactly is going on, because we're talking about orbitals here, which we'll talk about. We'll introduce it, but you're not going to get too much into it compared to 101. That's where you get really into this. Okay. You guys remember this? Right? Pure substance, we're talking about just one type. You have elements. What can't you do to elements?
Break them down.
Break them down. Then you have compounds. The way you form compounds is you have elements coming together in a specific ratio to form compounds. What is this process called? Yes, correct. Chemical reaction. So you're able to go in this direction, a chemical reaction has occurred. You can go in the opposite direction, chemical reaction can happen there too. So it can go in either direction. So notice you can do that with compounds, but again, elements, you cannot break them down any further. Periodic table of elements. Meaning they still sustain the properties of matter. Because remember, a pure substance is part of matter. Okay, now we're going to further classify each one. So we're going to get down here. We're going to look at each one. Now, one of the things you should notice, there's a word that appears twice.
Molecular.
Yep. Molecular shows up twice. So we're going to look at each one. Atomic. Now, when you're looking at all these words, just think of what they mean. Atomic. What word is in atomic? Atom, yeah. Use the word to help you. Now, molecular, you're talking about a molecule, right? Another name for molecular on this side, to kind of keep it different, is covalent. So this is the two guys sharing a dinner. So that could be used here instead if it's confusing for you to have molecular on both sides. Then you have ionic, which we'll look at. This is the proposal. So we're going to look at each one. If I look at this first one, we're dealing with elements, right? Yeah. Elements. So if it's atomic, we're just dealing with that particular element. And notice it's one atom, right? Now here, what do you notice the difference?
It's more than one, but it's the same one.
It's more than one, and notice it's fused together. So here, it's behaving like a molecule because there's more than one thing, more than one atom involved. So here, they're fused together. This is molecular, but it's still an element because you have the same kind. So when we talk about oxygen, right, oxygen gas, you need to survive. Oxygen gas is actually a molecular element. It's always two of them, never one. Oxygen, O2 gas, is always O2. It's diatomic. Diatomic. Two atoms fused together every single time. So you can see that here, diatomic. And that's what it says there. So here's atomic. Notice they're right next to each other, but they're not fused together. So that's just atomic element. Look at chlorine. You have two of them fused together. So this is diatomic. This is by itself. You can even call it monoatomic if you wanted to. So that is the actual atomic element. This is the molecular element. Now, how do you know if it's going to be fused together like this? There's 7 of them that will always be diatomic. And keeping, I can't do this, but the way to remember these is have no fear of ice cold beer. Have no fear of ice cold beer.
How does that work when you start with the above it?
They don't have it in the right order, but you would write it in the right order. But if you look at it, have no fear of, you have ice, and then cold, notice you have CL, and then beer, you have BR, right?
Maybe we just remember the beer.
Remember the what?
Maybe we just remember the beer.
Yeah. Or, if you look on the periodic table, those elements, the 6 of them, make a 7, right there. And then the last one is hydrogen. So they actually make a 7. And then you just have to remember hydrogen. So, this weekend, don't drink too much beer, but have no fear.
I feel like he did some smart ass comment or something. Yeah.
I have these notes.
Oh, you do?
Yeah.
Do you think they're better? Do you think they're better than these?
I'm going to look at them.
Make sure to start the homework.
I feel like if I would put my pity on me,